welcome to today's physics seminar talk in the Wichita State University Physics Seminar Series, funded by Eddie and April Lucas. Though we didn't have a lot of travel expenses to reimburse, with mostly virtual talks this semester. Oops. So today we have Greg Palowski talking about the DUNE experiment, and he has been an undergraduate here in Wichita. He then went on to graduate school at Rice University. He's now at the University of Minnesota, but also on sabbatical back here in Wichita. So please help me welcome Greg Palowski.
Okay, thank you, Holger. Yeah, as mentioned, I'm used to be an undergrad here, and I'm now a visiting professor for this academic year. So it's been nice to be back, although it's been a bit of surreal experience with COVID. So I haven't really got to interact with people. But you guys did give me a nice office space, and I'm currently sitting in the basement of Jabara right now for this talk. So it is a nice space. Maybe if the vaccines go well, the last month of the academic year in May, I might be able to interact with people. But why don't we talk about some of the physics I'm doing? So while I'm here, I've been doing some work with Holger and Nick. But I'm also still doing research in neutrino physics on the DUNE and NOVA experiments. And I want to talk about those experiments. And so when I initially signed up for this talk, I said, oh, I'll be talking about the DUNE experiment. And so the title that was put down was Physics with the DUNE Experiment. But actually what I'm going to be talking about isn't the standard neutrino-based physics that's done with the DUNE experiment. I'm going to be talking about other physics that's going to be done with the DUNE experiment, not the neutrino related. And there's actually a few different things you can do other than neutrino physics on DUNE. And what I'm actually going to be talking about is related to proton decay and the changing of a neutron to an anti-neutron. So this has never been seen before and be physics beyond the standard model. And it actually would be indications of what are known as grain unified theories. And so I'm going to be talking about physics with the DUNE experiment, the motivation for it, and what we could possibly see with DUNE. Now, before I go into that, though, it's probably still important to at least talk about what the DUNE experiment is and how it relates to neutrino physics. So in case you're not aware what DUNE is, it's this collaboration of over 1,000 physicists, and it spans over 30 countries. So it's a large international effort. The primary goal is to study neutrino oscillation phenomenon. And so as many neutrino experiments go, the experiment's name is an acronym. We're pretty unimaginative. We use probably an excessive number of acronyms. But DUNE stands for the Deep Underground Neutrino Experiment. And so as you can imagine with deep underground, the primary detector for the DUNE experiment is underground, and it's deep underground. It's in this old mine at the Sanford Underground facility in South Dakota, probably about half an hour away from Mount Rushmore. And it goes 1.5 kilometers deep underground. And the point of this is that it's going to reduce backgrounds if you go deep underground, and I'll explain that later. And the primary goal then is to produce neutrinos at Fermilab. It's this high energy physics laboratory that's in Illinois, where they produce a beam of neutrinos and they shoot it towards this mine in South Dakota. And the neutrinos rarely interact. I'll talk about that later, but you can actually send them through the Earth, trillions upon trillions, and a very tiny fraction interact with the Earth, and an even smaller fraction interact with the detectors that we have underground. And so the reason why we're deep underground is because it reduces backgrounds that I'll talk about later. And you need low backgrounds because if neutrinos rarely interact, you're not going to have very many interactions when a neutrino finally interacts in your detector, and you don't want to be overwhelmed with backgrounds. And then because they rarely interact, if you double the mass, you basically double the probability they interact. We have huge, massive detectors to detect these neutrinos. And then the primary goal is to shoot a matter version of neutrinos for the Earth and detect how they transform from one type of neutrino to another type of neutrino, and then send an antimatter version, and to see if that probability of it changing from one neutrino type to the other is the same for matter and antimatter. And if we see a difference, then this indicates an asymmetry between matter and antimatter that isn't normally found in the standard model, and could help explain why there's matter in our universe. And this experiment isn't running yet. So the goal is to have, the first FAR detector module running in 2024 and beam running in 2026. Now, maybe there'll be delays. The official line is it starts 2024, but what impact does COVID have, stuff like that. So I'll just say that it's going to start near the middle to the end of this decade. So what I'm going to be talking about is what potentially could happen with the DUNE experiment. Now, I started talking about neutrinos and sending those particles. And if you're not aware of what a neutrino is, you might find this talk a little confusing. So I figured I should, step back. And in case you're not familiar with high energy physics or particle physics, just give you an overview of what's involved with that and the particles that are involved. So in the field known as high energy physics or particle physics, we're interested in the building blocks of the universe. And that's the building blocks for matter, and not only matter, but the forces that allow the interactions between the matter. And what we discovered is that the forces and all the matter in the universe can be described by just a handful of elementary particles or fundamental particles, in which you have particles called bosons that mediate the force, that the particles exchange bosons back and forth virtually in quantum mechanics, and that leads to a force. So you have, for instance, a photon, which is the carrier of the electromagnetic force, the gluon, which is the carrier of the strong force. The strong force is the force that binds protons and neutrons together in the nucleus. And the electromagnetic force is the one you're probably familiar with of magnetism and electricity. It binds the electron into the atom. And then we have this Z boson and W boson. They're associated with what we call the weak force. And I'll get into that a little bit later with how it's related to the neutrinos. And then you also have a Higgs boson, which is the particle that gives mass to the elementary particles. And then you have particles known as fermions, in which they're organized in generations, where basically there seems to be a heavier version of particles, where you start with the lowest generation, the lightest particles, and you get heavier versions. And things decay down from heavier that have more energy to the lower energy things. And so most of the stuff we deal with in everyday evolve the lower generations of matter. And so you have quarks, which are particles that make up protons and neutrons, and a proton and neutron is made up of 3 quarks. And when you have 3 quarks, we say that you have a baryon number of 1. So baryons are made up of quarks. And what we've noticed is with all the physics processes that we've seen is that you always seem to conserve baryon number, this intrinsic quantum number associated with these 3 quark states, where no matter what the interaction happens, you always retain a 3 quark state with a baryon number of 1. And so we say, like, this appears to be a conserved quantity. So for instance, protons appear, we're going to be searching to see if they do disappear, but they appear to be stable and survive forever, even though they're heavier than photons, they're heavier than electrons, they don't decay down to those lower energy particles. So there seems to be something that keeps them there. And we call that, okay, there's a baryon number. Protons have a baryon number 1, and that's a conserved quantum number. And then neutrons have a baryon number 1. And whenever a neutron decays, it decays to a proton. So it conserves baryon number. And so that seems to be something that happens, that you have a conserved baryon number. And I keep on saying baryon number a lot because this will come up when I talk about proton decay and why we care about it. All right, and so you see that this conserved quantity proton number. There's also antimatter versions of things with opposite charges, and so they have opposite baryon number then too. And so the antimatter version of a proton, antimatter version of a neutron has a baryon number of -1. And as far as we can tell, these numbers seem to be conserved quantities. And then you have the leptons. And the most familiar one we have is the electron, which we have in our atoms. And then you have heavier versions, the muon and the tau. And those are heavier, they decay and eventually decay to electrons. And that's why we're most familiar with the electron. And then there's these associated particles with the electron, muon, and tau, which are neutral, called neutrinos. And then you may not be very familiar with neutrinos, and that's because they just really don't interact very often. They're very weak. But it's a little disturbing that we may not know much about them because they're actually one of the most abundant particles in the universe. And yet they're one of the least understood particles in the standard model of particle physics. So theoretically, we've known about them for around 100 years. And there's the second most abundant particle in the universe. The most abundant are photons, the cosmic microwave background that fills our universe. That's the most abundant particle. But right after that, and it's actually very similar magnitude of number, you have neutrinos. And so if you were to go out in empty space, and I mean like empty space, out of the solar system, don't get any of that solar wind and all that stuff. You go in empty space, there's still matter there, and you're going to have on average on order of 100 million neutrinos occupying a cubic meter of empty space. And you also have neutrinos constantly produced in nuclear reactions. So in the sun, for instance, you'll get 100 billion of them passing through an area the size of your fingernail each second. These are neutrinos being launched out from our sun. All right, and so they're very abundant, but you don't know a lot about them. We, and even particle physicists don't know a lot about them, and it's because they're weird. And their two biggest features that make them weird is that they don't have electrical charge or color charge, where color charge is the charge associated with the strong interaction. And so it doesn't undergo electromagnetic or strong interactions, and they have very tiny mass, so they almost act like massless particles. And because of these features, the only way we really experience neutrinos is how they interact through gravity and the weak force. And gravity is really weak. These are very tiny massive particles that you don't really see the gravity at the particle level. The only way we've observed gravity for neutrinos is when you add up tons of them, basically on a cosmological scale, and you see how neutrinos influence the cosmological structure of the universe. And that's really the only way you see gravity for neutrinos. And then at the particle level, it's just so weak, it's negligible. And at an individual particle level, the only way you really see a neutrino is how it interacts with matter for the weak interaction, which it exchanges one of these Z or W bosons. And these Z and W bosons are massive. They have mass, and their mass energy is greater than the typical energy of a neutrino. And so what that means is, you're kind of violating energy conservation by creating a boson to transfer. So this has virtually, for quantum mechanics, basically you could kind of view it hand waving as the Heisenberg uncertainty principle, where if you can have energy for a very short period of time. And so all this means then is that, okay, this can happen quantum mechanically, but it's very suppressed. And so this interaction rate happens at a very low level. And you kind of view these interactions as discrete interactions where this exchange happens. You don't really view it as a continuous force, like, if gravity, I feel myself constantly being pulled down, continuously being pulled down. While with this weak interaction, you kind of view it as just, discretely happens that, at some given random time chosen by quantum mechanics that this particle gets exchanged, and there's an interaction between these things. Now, this force is the reason why we have flavors known as electron neutrino, muon neutrino, and tau neutrino. And that's because when you have a weak interaction which you exchange a W, the neutrino changes into one of those charged leptons. So electron neutrino changes into electron, a muon neutrino changes into muon, and a tau neutrino changes into tau. But you also have these Z bosons, which produce what we call neutral current interactions. And in those interactions, the neutrino doesn't change its type. It remains a neutrino when it interacts with something else. All right, so this is why we have 3 neutrinos in that table and why they're labeled electron, muon, and tau, because they couple through the weak interaction to the charged leptons. But then again, these are massive bosons, typically with a mass energy much greater than the neutrino energy, that these are highly suppressed interactions. So they rarely happen. So typically, when you have a neutrino of typical energies, I mean the neutrinos that we get from reactors, for instance. So, a few MeV. At those energies, typically, the neutrino will just keep on traveling through a slab of lead, and it'll keep on traveling near the speed of light, and it'll take about, a year before it has some probability to have, interact, about 50% chance of interacting. And so it's very rare for a neutrino to interact with matter. It usually just passes through it. Now, not all neutrinos, take exactly 1 year of traveling through material before they interact. This is, a quantum mechanical process. There's some probability that a neutrino will interact with matter anywhere along this path. It's just the probability that it happens. So what could happen is instead of sending 1 neutrino, you send, trillions upon trillions of neutrinos, and then there's some probability, 1 might interact right here, 1 might interact here, and so forth. And then you can build a finite detector with, this intense neutrino flux unit and have some probability that, a neutrino out of all of those, a very tiny fraction, will interact. And then if you double the amount of material, you double the amount of targets, you double the amount of times an interaction can happen, you expect to see twice as many neutrinos. And if you double your neutrino flux, you expect to see twice as many neutrinos. So the idea is have big, massive detectors and intense neutrino beams to have any hope of seeing anything. All right, so this is why then you can send neutrinos through the Earth, because they rarely interact and we need a massive detector. And then the fact that they rarely interact and we're constantly, being bombarded by cosmic rays, which I'll explain next, is why you put this underground so that there's very little background so that you can spontaneously see a neutrino interact in your detector. Okay, so I've been mentioning that steep underground because it lowers backgrounds. So what are these backgrounds that disappear when you go underground? Well, they're cosmic ray backgrounds. So basically, at the surface of our planet, we're constantly being bombarded by cosmic rays. So what is, or at least particles that are created by cosmic rays. So what is a cosmic ray? It's usually a proton that comes from some unknown source from outer space. So since we don't know the source, we say it's a cosmic source. It just comes from the cosmos. And then it hits the atmosphere. And these are really energetic, that they have enough energy in the collision through E equals mc squared to make masses of other particles. And so in these cosmic ray interactions, you'll get other particles being created. And then these particles end up producing muons. And muons live long enough, especially when you take into account special relativity slowing down their lifetime since they're moving near the speed of light, that they can reach the surface. And muons are really massive, 200 times the mass of electron. So they kind of just plow through material. And so they could even penetrate through mountains, through the ground, but they lose energy as they go through material. And so the deeper and deeper you go underground, the less likely a cosmic ray muon is going to hit you. And so this is a pretty intense rate. If you stick your hand out, you get about every second 1 cosmic ray going through an area the size of your hand. And so if you imagine you make these giant detectors, and our detectors are like the size of buildings, you get a substantial amount of muons, passing every second. While you're not getting a neutrino interaction happening every second. So you want to go underground and reduce this. And these are fairly significant. They do result in about 10% of your daily radiation exposure. I think most of it comes from radon. And if you were to go up higher, you get more. I've heard stories. I don't know if it's true, but I've heard stories that flight attendants, since they're so high, their daily radiation exposure is mostly cosmic ray. From cosmic rays because they're flying up so high. Right there's a plane right there, so they're getting hit. So unless you're a flight attendant, your daily radiation exposure is only 10% for cosmic rays, and the majority comes from radon. Okay, so that's why you go deep underground. And then we need these massive detectors because neutrinos rarely interact. So you make these huge massive detectors. What we're going to do for DUNE is we're going to go under this mine 1.5 kilometers, and we're going to build 4 modules full of liquid argon. So why liquid argon as opposed to gaseous argon? Well, you need a lot of mass, a lot of targets for a neutrino hit, and liquid is 800 times denser than gaseous argon. So it fills in a smaller volume for the same amount of mass. And then the idea is that we'll have 10 kiloton fiducial volumes for each of these, so a total of 40 kilotons. Fiducial volume just means that when we have a neutrino interact, we want to see all the particles that come out of the interaction, that the event has to be completely contained. And if it were to happen on the edge of the detector, a fraction of the particles produced would escape, and you want to be able to accurately measure it. So you can't use all of the argon. You have to use some interior argon. So we'll actually have about 70 kilotons of argon, but we'll effectively only use 40 kilotons where we could actually measure stuff with. And then that mass has a lot of protons and neutrons. So in order of 10 to 34 protons and about 30% more of neutrons. So a lot of targets for neutrons interact. Now, what I said is I'm interested in using DUNE to look for proton decay and neutrons turning into antineutrons. So this means that this volume is a big source of protons and neutrons. All right, and then this is liquid argon. Argon's a noble gas. It wants to be a gas. So you have to make it really cool. You have to get below 90 Kelvin to make it a liquid. And the way we do this is these modules are cryostats that you then fill with the liquid argon, and then the cryostats are insulated to keep it cool. And you can see here a prototype detector of a DUNE module. This is at a lab CERN in Europe, in Switzerland, in which this is set up. It's a prototype. It's 1/20th the size of one of the actual modules that we're going to have underground in South Dakota. And it's about half the size. The actual one will be twice as tall as this. And if you look at it, you can see that there's a membrane, and that you can see that it has these grooves and ridges and things fold here. And that's because, this is at room temperature. When you add something around, less than 90 Kelvin, things are going to contract. And so this membrane is designed so that it can contract and not rip apart. And then what you have is, for our electronics, you have entries in the top that I'm pointing at here, where the electronics can come through to read out things that detect neutrinos in this volume. And then also you can vent out argon, because things don't stay cold, they get warmed up, they'll turn into a liquid, will turn into gas. That increases the pressure. You need something to vent out, otherwise you would have an explosion and stuff like that. All right, so this is the kind of system we have to get giant cryostats to get cool liquid argon, and then the liquid is massive. Now you might be saying, well, all right, so you just did liquid argon because you wanted mass. This is really an expensive way to get a lot of mass. We could just take a slab of iron and a bunch of iron, and we could quickly get mass in a small area, and it would be way cheaper than making liquid argon. But the problem is, if a neutrino interacts in a giant slab of iron, how are you going to see the interaction inside that iron? You're just going to see a slab of iron. You can't peek inside of it. And so there's a desirable property with liquid argon in which that you could see the interactions that happen inside it. So what happens is you take this liquid argon cryostat and you put planes in it. So you have a cathode plane and an anode plane. You charge them up, so there's an electric field between them. They're at a high voltage. And then what happens then is a neutrino could come through this material, hit the argon interact and produce charged particles. And then when it does that, you get this animation here where a neutrino interacts here. It produces charged particles that shoot out. And those charged particles, what they do when they travel through the argon, they ionize it. They release electrons. And those electrons see this electric field and they drift to the anode wires that you have. And so what we have then is this strong electric field pointing from one plane to the other. There's a space of 3.6 meters. And then what you do is you pick up the electrons that happen through this ionization. So you can see an image of what's happening inside this massive detector. And so that's the reason why we use liquid argon, because we could get a huge mass and you could see what's going inside of that mass. And the way this works is that the drift velocity of these electrons are constant. And so if you know the time that this interaction happens, then the time it takes for an electron to hit these wires, the velocity is constant, corresponds to the distance. So by measuring the time it takes to get a signal on these wires, you can figure out the position of these particles, where they were in the left-right direction. And then we have wires that are oriented different ways. So we have these vertical wires. When charge comes and you see it on one of these vertical wires, that tells you then where it is in a position in and out of this page. And so by getting a signal on one of these wires, you know where it is in and out of the page. Based on time, you know where it's left, right. The only other dimension you need to figure out where this particle was that ionized these electrons is up and down. And the way we do that is by getting these wires that crisscross in this pattern. And then by having hits on these crisscrossing wires, you're able then to determine where it was in three-dimensional space. And then the idea is that these nanowires, you have three sets. One of them actually collects the charge. It's known as a collection wire. And then the other ones that are neighboring are really close, that when those charges get collected, they get an induced charge on them, and you pick up a signal from that induced charge. All right, and so maybe another way to show you is there's this nice video that Fermilab made that shows you what happens when a neutrino enters the liquid argon detector. So they'll have neutrinos coming to the detector. One of the neutrinos out of all of them will interact with an argon atom, and it'll do what we call charge current interaction. It's a muon neutrino. It will produce a muon, and then it'll change a neutron into a proton. So then the muon and the proton goes shooting off. They're charged particles. They ionize the argon, producing these electrons that then drift, and then we could basically get the direction of these tracks and their size based on the signal that they leave on the wires. And then the other thing to note is that to ionize the argon, to liberate these electrons, it takes energy. Where does that energy come from? It comes from the kinetic energy of these particles. So these charged particles that get produced, they lose kinetic energy to form these electrons, these drift electrons. And basically the number of electrons they liberate is proportional to the amount of energy they deposited. And eventually they stop once they deposit all their kinetic energy. And so by measuring the total amount of charge, you can measure the energy that's deposited by these things. And so you know the energy of the muon, you know the energy of the proton. And also, if you get a lot of charge in one spot, that means it deposited a lot of energy in that one localized spot. While if you have less charge in other spots, it means it's less localized. So you could get a measure of the rate at which it's depositing energy too. And so this method allows us to measure the energy of interactions that, you know, seem to magically, spontaneously happen inside the middle of the detector, and identify the individual particles that make them up. So what this means then is, I guess if I go on to my next slide, is that you get these a huge mass, and you can make a nice image of the interaction that happened in there. So this is an actual image from our prototype detector in Europe, in which there was a cosmic ray that interacted with the detector, the cryostat, and it created a shower of particles. And so you can see the individual particles, we can measure their energy and momentum, and the color is an indication of how much charge, how many drift electrons got liberated, and you can see the intensity of energy. So these seem to be electromagnetic showers that are created. And then while you have other things that we call minimum ionizing particles, so things are like a charged pion or a muon. And while an electron is much less massive than a muon, it scatters and produces what we call an electromagnetic shower. Oh, and I forgot to also mention a charged pion. Charged pions are made of, and neutral pions are particles that we call mesons, and they're made of quarks, and they're made of 2 quarks, so they can weigh less than a proton or a neutron, which has 3 quarks, but they contain 1 quark and 1 anti-quark, and so their baryon number is 0 then, because they have an equal amount of matter and antimatter, even though they contain quarks. But then and the only reason I mention mesons is because I'll reference them later, but they're a form of matter made by quarks. All right, so you can see then that we have these massive detectors. They're underground, they have little background, and then you can see basically particle interactions that spontaneously or appear to spontaneously happen inside the detector with very great resolution. So this is great for neutrino detectors. It's also great then for looking for proton decay and neutrons becoming antineutrons, because those will spontaneously happen in your detector. They're huge, so you have lots of protons, lots of neutrons, and they're low background. So you can see like, oh, this event suddenly happens, and it seems consistent with a proton decay or neutron decay. All right, so now, why bother looking for proton decay or an anti-neutron to neutron oscillation? Well, the reason is because there is some physical motivation for that. And it kind of follows from basically a tenet of physics that I think a lot of physicists have. I don't think this is a formal rule, but I think a lot of physicists kind of hold this, in the back of their mind, especially particle physicists, that there's this belief that all physical phenomenon is just governed by a few simple rules and symmetries. And then based on these simple ideas, you can explain everything. Now, maybe working out the particulars of everything becomes really, really complicated, but it all goes back to some really simple ideas. And so one idea is, like, for instance, if you have some symmetry, it results in a conservation law. So conservation of energy, momentum, stuff like that, that you could say we have a universe that obeys these conservation laws because of a symmetry. And so that comes from Noether, who had this theorem about this. And so just to give you an example, of an idea of like, oh, we just have, one simple rule and a symmetry, we could use an example of quantum mechanics, where in quantum mechanics, we could say, okay, we have this rule, which the time evolution of some state of anything obeys the Schrodinger equation. So that's our rule. I don't know if there's a symmetry associated with that, but let's just call it a rule. All right, so this is how things evolve through time in our universe. So they obey the Schrodinger equation. And then we'll say, oh, in our universe, we'll also require it to have this symmetry called Lorentz symmetry. So basically special relativity. And in particular, the relationship between energy and momentum. If you require these 2 things and you start writing down equations that describe things that obey these 2 rules, you could come up with what's known as the Dirac equation. And if you come up with the Dirac equation, you end up saying that, oh, in a universe that obeys just this rule and this symmetry, I can have particles in that universe that have to have spin 1/2. So basically you have a particle that has to have an intrinsic spin to it, and it's a spin 1/2. And we do have those particles in our universe. And not only that, you'd say, oh, and there's a set of particles that have positive charge and negative charge, that there's a matter version of these particles and there's an antimatter version of these particles. So by just applying this symmetry and this rule, you end up saying, oh, if that universe obeys that, that universe can have spin 1/2 particles, intrinsic spin, and there's matter and antimatter in that universe. And similarly, you write another equation, you get what could be what we call the Klein-Gordon equation. And you say, oh, there could also be spin 0 particles with matter and antimatter in that universe as well. And so just kind of example, you start with something simple and then other things follow from that. And so the idea then is that, our universe, we just start with these symmetry laws, stuff like that, beautiful, all good things. And then all the laws of physics follow from that. And so you can imagine then that, we start with, this elegant, highly symmetrical universe. You have some, let's just say in a scenario, some initial field that has potential energy, and it releases that energy, goes to kinetic energy, expanding the universe. The energy goes to creating matter and antimatter. We have a symmetrical universe. We have the same amount of matter, same amount of antimatter. They interact with each other, annihilate, create particles, annihilate, create particles. But as the universe expands, they lose energy. And so when they annihilate and make new particles, they don't have enough energy to make the heavier particles. And so as the universe cools and it spreads out, they annihilate. And then when they make particles, they only make lighter particles. They keep on going, making lighter particles. And then eventually the only particle they have enough energy to make is photons, which have no mass. And then you end up with a very cool universe that just has photons. They're very cool photons. And by cool, I don't mean, rad or awesome. I mean low temperature photons. And, that's your universe. It's basically a microwave. Now, I have to put a caveat here that I'm just trying to emphasize that this highly symmetrical universe, you'd basically, with equals amount of matter and antimatter, you would just have photons left. The exact structure and temperature would depend on, the rate at which the universe expands. And if you don't have matter, you just had photons, the universe would expand faster. So don't take these numbers too seriously, or the exact structure I'm showing here. But the idea is that you just have this universe full of photons. And so if you think about that, that's a pretty boring universe. If it has no matter, all the stuff I own is made of matter. So it really sucked not to have any matter. Also, I wouldn't exist, so that would probably suck as well, not just not having stuff. And not only that, so there's no matter. It's a pretty boring universe. It's basically just a microwave. It's a pretty lame microwave. If you had some trans-dimensional being that enters this universe and says, oh, a giant microwave, and they throw a burrito in it, these microwaves are really cool. It's good to freeze their burrito instead of cooking their burrito. So not only is there no matter in the universe, it's just a giant microwave. It's a really crappy microwave at that. All right, but we live in a happening universe. There is actually matter there. So there had to be some asymmetry that created more matter and basically more baryons, so that you had protons and these protons being formed, and then the protons merging to make nuclei, and then eventually things get cool enough that the electrons can circle around that nuclei and make atoms, and then you have chemistry and things collapse and you end up getting our galaxies and planets, and you get the stuff that I have in my house then, which is the main goal of this expansion of the universe, is for me to get stuff. All right, so we have this happening universe, and it looks then that you had to have this asymmetry that happened. And so we kind of get this idea then, well, okay, we say like we want the laws of physics to be really symmetrical, but doesn't that mean we have a really boring universe? Don't we have to have an asymmetrical universe to have anything exciting happen? And then the idea is like, well, no, you could still have an underlying symmetry. It just gets spontaneously broken, especially, when things are hot and they go cold. You'll get things that are basically symmetric, but when they get cold, you also see a spontaneous breaking of that symmetry. So an example, for instance, would be, have a bunch of magnetized needles, and it's really hot. The needles are vibrating in all random directions. There's no overall magnetic field. And if you're out in empty space with these needles, there's no preferred up, down, left, right, back, forward direction, that all directions are equally the same. You have no particular direction. But, as the temperature decreases, these magnetized needles are going to vibrate less and less. And then eventually just randomly, maybe a quantum fluctuation or whatever, they just have that happen at a given instant when they're cool enough, a net magnetic field in a certain direction. It just randomly happened that they were pointing there that way at that time. And then because it's so cold, there's not enough thermal energy to cause the random vibrations that the other needles line up with that net field. And then as things get cold enough where they're not vibrating more, basically all the needles are lined up pointing in one direction. And so even though there was no reason why it preferred that one direction, just because things got cold enough, it randomly had to choose some direction and had to fall into some state. It just randomly happened to point some way. And so you could get an asymmetry that happens even though fundamentally things were completely symmetric. And so that's the idea, is that, okay, we can live in this highly symmetric universe, but then as things got cooler, there's a breaking of the symmetry, kind of similar to that. And then, that creates the interesting things that we have in our universe. So then you could say, okay, well, we can still make these theories and we just have to break the symmetry. But then when we go about breaking the symmetry, we have to fulfill some conditions. And so this is where Mr. Sakharov pops out. I'm assuming this is him. I've never seen him, saw him in person. I Googled searched him. This image came up a lot, so I'm assuming this is his actual photo, but it could just be whatever Google shows a lot whenever you type in this name. But I'm assuming this is Mr. Sakharov. He pops out and says, okay, I have 3 conditions that you have to fulfill when you break the symmetry in order to get matter in your universe. So one, you have to have baryon number violation. So it's basically kind of like a self-definition that, in order to have protons in your universe, if you started with an equal amount of protons and antiprotons, so 0 baryon number, that you have to have some baryon number violation so that you have protons each with a baryon number 1, some net positive baryon number in your universe. And then also, if you have more matter than antimatter, initially you had equal amounts, that you have to have something that violates the matter-antimatter symmetries, what we call C and CP violation. So they're kind of self-definitional, that you have to achieve those 2 things. And then the third thing, which maybe you don't think about, is that when this happens, it has to happen out of equilibrium. So what does it mean? If we live in a symmetrical universe, there's interactions that cause things to go one way. You have similar interactions that cause it go back the other way. And so if everything's in equilibrium, they'll bounce back and forth. And so even though at one time you might get more matter than antimatter, eventually, things would swing back the other way and there's equal amounts. So what happens, for instance, is you could have maybe it's our expanding universe is the reason for this, that things expand so much that initially things were dense, they interact, they produce this imbalance, and then things expand, they're less dense, and they're not able to interact at the same rate. And so they can't go back to what they originally were. And so you kind of lock in this imbalance because you moved away. Or you can kind of view it as you had a hot temperature, you had your random magnetic needles pointing in any direction, but once you got cool enough, then it can't go, there's not enough thermal energy to randomize things again, and it can't go back. So it passes some area where it can't do the reverse thing anymore. And so if we have an expanding universe, potentially doing number 3, then to get points 1 and 2, you could have what are known as grand unified theories that satisfy those 2 conditions. So what are grand unified theories? So the idea of a grand unified theory is that all the forces that we have are the result of some type of symmetry. So let me explain what. Let's use an example here. So let's imagine we're in a universe in which particles have intrinsic quantum numbers that can be represented by a positive, negative, and 0 value scalar. And let's just call that quantum number electric charge. And so imagine that electric charge is locally conserved. So that means that we're going to make this universe and say, this thing that I'm calling, associating as a quantum number, I'll call electric charge, I want that to be conserved. Then because it's conserved, we have from Noether that there must be a symmetry for that conservation law. And so then mathematically, this is it, probably the typical symmetry you think about when you see an image and you look in a mirror and say, oh, mirror symmetry, something like that. This is a very mathematical symmetry, and we call it a U1 symmetry when we write the equation. So a U1 symmetry is the symmetry that corresponds to this scalar number being conserved, the scalar number quantity being conserved. And so we say, okay, the universe obeys U1 symmetry, and if we assume it's, locally symmetric, another mathematical term here, but it's a type of symmetry and require them to be local, then that local symmetry then requires that photons have to exist. So we didn't even have photons in this model, but we just required the symmetry. And then by virtue of having the symmetry, you have to have photons in that universe. And furthermore, those photons mediate interaction between the electrically charged particles, and we call that the electromagnetic force. And what we end up finding is that all the forces, the electromagnetic, the weak, the strong or color force, depending on what you call it, come from these mathematical symmetries of a U1 symmetry, an SU2 symmetry, and an SU3 symmetry. And so the idea then is that you could have something beyond our current standard model of these separate symmetries for these individual forces, that there's some grand unified theory in which you have one great underlying symmetry, and that these individual symmetries, these individual forces just emerge from that greater underlying symmetry. So maybe from things spontaneously breaking or something as things get cooler. But there's actually just one big super symmetry that these all emerge from. And so in these grand unified theories, they predict things like baryon number violation, which is needed to have more protons in the universe than having just only cosmic microwave background and no protons at all. And so, they predict then that, protons get to decay, and then protons have a baryon number 1, they decay to leptons, 0 baryon number, that this would violate baryon number by 1. So this could happen in these grand unified theories. And also with certain conditions, you can get grand unified theories where a neutron goes to an anti-neutron, and neutron has a baryon number 1, anti-neutron has a baryon number of -1, it's antimatter, it's the opposite, that's a change of baryon number of 2 units. But these are possible grand unified theories. And these are really attractive theories because, it's just, you have this, let's call it a simple symmetry, maybe not really simple, but, this nice compact symmetry. And then it explains so many things, things just coincidentally happen to work out just right. That seems so coincidental for something so simple to work that people say, there must be some truth to this. And, that's probably one of the driving factors for it, for something so true to fulfill so many things. It just seems like there has to be some truth to it. And these grand unified theories really got some, go ahead back in the 1970s, in which probably one of the first grand unified theories you have was to say, oh, there's this SU5 symmetry. And from that, you could then get these emerging U1, SU2, and U3 symmetries, the ones that we have in the standard model. And in this SU5 symmetry, it predicted that protons decayed, and that they would decay with a lifetime of 10 to the 30 to 10 to the 31 years. Now, just to put that in comparison to the lifetime of the universe is 10 to the 10 years. So this is way longer than the lifetime of the universe. But you can still see it. Just because this is lifetime, it doesn't mean every single proton in the universe decays after this many years. It's a quantum probability. So if you get 10 to the 31 protons, then you expect on a type scale of a year, to see at least one proton decay. And so if you just get a lot of protons together, then you might see one of them decay. But it's very rare, saying, a handful over a year, that you need very low backgrounds over that whole time so that you only see that proton decay and don't have it overwhelmed by other things. Okay, and so then in that time period, this drove a lot of experience. There were a lot of experiments. I'll just talk about one because it happened in Minnesota, in which they went into a mine, so they had low backgrounds. They had a fairly sizable detector because they didn't need a huge proton lifetime for what was predicted in this model. And, they made a measurement of 10 to 30 years. So it kind of ruled out the lower part of that theory. And then there's more experiments. They got bigger, ran longer, and so they have more protons over a longer time. They were able to get more sensitive, and eventually they ruled out that theory that was introduced. And currently what we have is from the Super K experiment. It's full of 50 kilotons of water. The fiducial mass is 22.5 kilotons. They've been running for a very long time, so they have an exposure of 0.37 milliton years worth of proton data looking at for the decay, and they put a proton lifetime limit of it being greater than 10 to the 34 years. So about 1,000 times the mass of Soudan, about 1,000 times the lifetime limit. All right, so this rules out those earlier models, but you could still do grand unified theories that have lifetimes just above this or even higher. And the fact that these grand unified theories are very appealing theoretically, that they can answer so many things and also potentially give you a mechanism for baryon number violation. We still look for it, and so a key signature would see proton decay. And so in DUNE, we plan on looking at proton decay. There's usually two types of grand unified theories: supersymmetric grand unified theories or non-supersymmetric grand unified theories. And the supersymmetric ones, they tend to be dominated with protons decaying to a kaon. It's a type of meson, so a quark anti-quark system, and an antineutrino, while the non-SUSY ones tend to go to a positron and a pi zero, a lighter type of meson, so quark anti-quark. All right, so this one's been studied very heavily in Super K, this decay channel. But this one involving kaons, not so much in Super K, because they're a Cherenkov light detector. Cherenkov light detectors work by having a charged particle move faster than the speed of light in that medium. So nothing can go faster than the speed of light in vacuum, but light can move slower in a medium, and a charged particle can move faster than what light can in that medium. And that produces the equivalent of a sonic boom in light, Cherenkov light. And that's how Super K detects things in their water. These kaons are so massive, they're not moving faster than the speed of light in water. And so they don't produce the Cherenkov light. But you can see these kaons, these charged particles, in the DUNE detector. And so the idea in the DUNE detector is you have all these protons that eventually one of them will decay, and then it'll decay to a kaon and an antineutrino. The antineutrino will escape, but it has very low probability, extremely low probability of ever interacting with your detector. It escapes, and so all you see is the kaon. But because it's two particles coming from one, which was at rest, that these have to have equal and opposite momentum. They can point to any direction because it was at rest. So symmetry of the universe can point any way. But once one particle goes one way, the other particle has to go the opposite way with equal and opposite momentum. And then the sum of energy has to be equal to rest mass energy of the proton. And so that puts a constraint that exactly what the momentum of this kaon has to be. And so then it's a charged particle ionizing your liquid argon. It travels, it loses all its kinetic energy, it stops, and then it will decay because it's an unstable particle. And 64% of the time it decays to a muon in neutrino, and it decays to pions 21% of the time. We look at both of these modes, but let's just focus on this one. So then what happens in the case of muon? Again, it's a two-body problem. Something at rest, decaying to two bodies, equal and opposite momentum, and their energy has to sum up to the rest mass energy of kaon. Exactly what the energy of this muon has to be. And then it deposits energy that corresponds to a certain length. And then the muon stops, and then it decays with a three-body decay to a neutrino, an antineutrino, and a positron. And then because this is three-body, you have more distribution with the energy of these electrons, but you have a range of possible electrons. But you get this signature then that you basically suddenly see a kaon followed by this muon and followed by this electron. Now, the issue is that we can't make out the times of these particles because the electrons drift over the time scale of milliseconds, and this is happening much shorter timescales than that. So we can't resolve the times, but what we look is for three distinct particles being connected in this fashion with one leading into the other. All right, and so this is a fairly clean signature, but we do have a background, and the background comes from atmospheric neutrinos. So in these cosmic rays, the particles that could get produced eventually decay to neutrinos, and those neutrinos can go down as far as you want. Most of them will pass through the Earth, and they'll still hit our detector. And so there's a sufficient number of these atmospheric neutrinos that they produce a very large background to that proton signal. So what happens is you'll have a muon neutrino coming in from the atmosphere, being produced in the atmosphere there, comes in our detector, interacts with argon, and then it changes a neutron in the argon to a proton, and the muon neutrino turns into muon. So you get a proton shooting out and a muon being shot out. And so this kind of looks like a kaon going to a muon, and then the muon stops, and then decays the electron. It kind of looks like our signal, except the energies don't necessarily match up. But we have so many neutrinos hitting us that there's going to be some fraction of time, there's going to be a neutrino that produces energy for the proton consistent with the energy of the kaon, and an energy of the muon consistent with the energy of the muon that we expect for the proton decay, that there's just such a sheer number of atmospheric neutrinos hitting us that you'll get these energies matching up. Now, there's another way you could distinguish it in that the proton and the muon both leave the same point. They have a directionality. And as a charged particle stops, when it stops, it deposits most energy. So you should see less energy deposited here, more energy deposit at the end. We call this the Bragg peak. And the idea is you can determine the directionality, that in this case where it's a neutrino producing a proton, you should see a pulse of energy here. While in the kaon's going in this direction and then decays to a muon, you should see a pulse of energy there. So we try to use that to distinguish between these two signatures, but because of resolution effects, other bits of noise, it doesn't always work out that you can resolve that Bragg peak, and you can't always figure out the directionality. So we end up putting this information, the likelihood that what's the direction of this proton or this stub that's here, a proton or a kaon, is it stopping here or is it stopping here, to determine whether it's a proton or a kaon. Does the energy match up the kaon's energy? Does the muon match the expected muon's energy? We put all of those things into a boosted decision tree. And we then get a variable at this boosted decision tree that separates signal and background. And we choose it to optimize for setting lifetime limits. And the optimal value that we could currently get is a 30% signal efficiency. So selecting almost 1 out of 3 proton decays that would happen for a background rejection of these atmospheric neutrinos of 99.9997%. So that would result for a 40 kiloton detector recording for 10 years. So 40 times 10, a 400 kiloton year exposure to an expectation of 0.4 events over that 10-year time period caused by atmospheric neutrinos. All right, so 0.4 just means on average, you have Poisson fluctuations. Sometimes that will result in 0 background. Sometimes it results in 1 background, 2 backgrounds, stuff like that. That's what 0.4 means. But if you do that, then we have a sensitivity at 90%, where if we see nothing, we expect this set a proton lifetime limit of 1.3 times 10 to the 34 years. So that's kind of comparable to what Super K has right now. So we're not going to be pushing things past much past the current exposure. But the idea is we're looking at a different channel, so it's complementary. And then the other thought is that, we might be just at the edge of seeing these grain unified theories. There's going to be other experiments. You might see proton decay, and then we might be able to supply a complementary signal. Then the unfortunate thing is really to increase in exposure, you have to increase your number of protons by, orders of magnitudes to really go up to arbitrarily high. And, how do you increase these things by order of magnitudes? You need more protons, so order of magnitude more protons, or more exposure, more time that you're looking over, order of magnitude more time. So, after a while, there's limits to how many order of magnitudes can you increase the mass of your detector, and how many order of magnitudes can you spend looking at the detector? So spend a year, next order of magnitude, spend 10 years, next order of magnitude, spend 100 years, next order of magnitude, spend 1,000 years looking at this detector. There's limits to how far you could go with this. So hopefully, if there is a grand unified theory that leads to proton decay, it's not too much greater than 10 to 34 years if we have hope of seeing it. All right, so then I want to talk about another process that could happen that violates baryon number, in which a neutron oscillates into an antineutron. All right, so the idea is that neutrons are neutral, they have no charge, except for maybe baryon number. And so there's, nothing preventing it from going from a neutron to an antineutron other than the fact that there's this baryon number that has to flip sign. And so if we have some baryon number violation, this could possibly happen. And we have a lot of neutrons in the DUNE detector to look at. And this is a well-known signature, from ages ago in high energy physics. They looked at antineutrons and saw what they did when they annihilated with a neutron or a proton. So it's very well known what will shoot out. All right, and then the idea is that a neutron can do this oscillation in free space, but when you put it in a nucleus, there's a potential energy that makes it less energy favorable to happen. So for instance, a free neutron has a lifetime, it decays to a proton, of 880 seconds. But if you put it in a nucleus, it seems to have an infinite lifetime to be stable unless this procedure happens. All right, so that means putting in a nuclear environment really suppresses it from trying to change to something else. And so we get a suppression factor for being an argon, and it's a huge 10 to 23 suppression factor increase to this lifetime. And so these things will last much longer than they would if they were free neutrons able to oscillate. But you're able to calculate the suppression factor. It's fairly model independent of what happens with these oscillations. It just depends on the Hamiltonian involving the nuclear potential energy for neutrons and antineutrons and the mixing between them. And so you can correct for this. And the current limit we have is from super K of that this oscillation happens on a time scale of 2.7 times 10 to the 8 seconds. Okay, so what we do is we look for this. So the idea is that neutron will oscillate to an antineutron. Is an argon 40. You lose a neutron, becomes argon 39. 18 of those nucleons are protons, 21 are neutrons. So the antineutron can annihilate with any one of those. So has those probabilities interact with any one of those. But when it annihilates with those other particles, either proton or neutron, this is very well known what will be produced in their branching fractions. And what you see is you get an explosion of pions. These are these mesons, low energy mesons, that get shot out. And because these things were at rest, there's zero total net momentum. So these particles shoot out isotropically. And there's no preferred axis either. So they just all shoot out isotropically, zero net momentum, and the energy fueling them is the mass energy of the anti-neutron and the nucleon annihilated with. So the mass energy of two nucleons, which is about 2 GeV. And so it's a very nice signature you see where you get this isotropic explosion of pions. This shows the different views. With the way the views work, you're taking a 3D image, you're getting a 2D slice. You don't always get a preferred angle, which it's obvious to see. But fortunately, in one of these wire views, it lines up pretty well where you can see, okay, yeah, I can see these pions shooting out, and they are pretty isotropic in the way they shoot out. Their total momentum is around 0, and the total energy of these things is around 2 GeV. Now, unfortunately, there's backgrounds to this as well, again, coming from these atmospheric neutrinos. And in this case, it's from neutral current interactions. So when atmospheric neutrinos come in, they're coming in with a momentum. So they, the event does have a momentum to it, and that momentum, but in neutral current interactions, a neutrino is escaping, and then that neutrino can basically carry the net momentum and leave behind something visible that looks like it has no net momentum. And these go to high enough energies that what they leave behind can be around this 2 GeV. And so that means for these neutral current interactions, you can end up faking something that ends up looking like one of these isotropic 2 GeV pion bursts. And this ends up being a background. And then also our signal isn't the greatest purest signal either. That's because these antineutrons were trapped inside nucleus. So the original nuclei or nucleons had Fermi momentum. Basically somewhat like putting a particle in a quantum box. They're going to have some momentum to them. They also will interact with the particles in the nucleus as they escape, and so pions can get absorbed. So in these pion explosions where you're expecting pions, you go for cases where you have very little fraction of bits with 0 pions to getting a significant fraction with 0 pions because they got absorbed. The pions get scattered in the nuclear material, changing their momentum shown here, and you also knock out additional nucleons. So it doesn't look as clean as what you would expect. And so your signal is a little obscured. You have background that can fake it. And so we have to optimize these things. And we use a CNN algorithm. So these are convolutional neural networks. They're the same things that look at images of puppy dogs and cats and say, is this a cat or is this a dog? And the idea is you show them images of these events from simulation so it could determine, what signal, what's background. This alone isn't enough. So we take the score, feed it in with a BDT, boosted decision tree, where we also have reconstructed tracks and showers, their energy, momentum, and number, put that all in a BDT, and then it outputs a score of something that looks like background or something that looks like signal. And then to get the best lifetime limit, we need to have very little fluctuation from background. So basically no background. We cut really tight on this variable. We only have 8% signal efficiency for 99.98% background rejection. That gives us about 23 atmospheric neutrinos over 10 years of exposure of our 40 kiloton detector. But when we do that, we get a bound lifetime for this oscillation as 6.45 times 10 to the 32 years. And then if you take into account the nuclear suppression factor, that corresponds to 5.53 times 10 to the 8 seconds, which is 17.5 years. So you can see that nuclear suppression factor from it being bound is extreme because it goes from 17 years to 10 to 32 years. But we get this limit and it's about twice as good as what Super K has. So we could add more information there. And something to note, this really does no meaning. This is just a particular model that predicts, these oscillations. Nothing special about this model. They have different parameters they put in. And, for this limit, you're excluding a little bit of the parameter space. And if we were to get to 0 background and closer to 100 efficiency, then we would exclude, about half of that parameter space. But again, this is just kind of something cute to show. It doesn't really have too much meaning because I'm sure people can make any other models where they could say, oh yeah, we expect to see a lot of signal right where you're sensitive to. The idea is that, there are models out there that this will be probing stuff. And then just something I also found interesting is that, to put a context here, that it takes 17 years for a neutron, that isn't bound to oscillate to an antineutron. The lifetime of a neutron is 880 seconds. So that's the time it takes to decay to a proton. So this is occurring over a much larger time scale than a neutron lives. But again, this is all quantum mechanical. There's some probability, that this would happen in 1 nanosecond after a neutron being created. It's just, you need a lot of neutrons to see that. So just to conclude, the DUNE experiment could explore physics beyond neutrino physics, and that the huge mass of this detector and its low backgrounds being underground give it the potential to study extremely rare physics processes. And those processes could fundamentally change our understanding of the universe. Thank you.
Thank you, Greg. That was a really interesting seminar. I'm sure we'll have a couple of questions, and although we are over time, I think we can take a couple of them now. Just unmute yourself or type in the chat or whatever works.
Yeah, I was looking at your past seminar talks. I saw Matt gave a talk about some DUNE physics in the past, so sorry if there's already some overlap there.
No, this was very good because
repetition doesn't hurt.
This was very good because you stressed some of the non-neutrino stuff with proton decay, neutron oscillations, and that's some of the things that our students might want to know about, that you just don't have to do the neutrino physics when you join an experiment like this. You have the possibility to do lots of other experiments.
Well, all right, if we don't have any questions right now, then let's thank Greg again for this very nice talk, and have a happy Thanksgiving break, everybody. And see you for the last talk after the break before the semester then ends. Have a good rest of your day and see you next time.
Yeah, you should mention the talk is just the Neptune Explorer project is the next talk.
Right, so that should be another good one.
Okay.
Okay. All right. Thank you. Goodbye.
Thanks. Bye.
Thank you very
Bye.
much.